Welcome to Mr. Enders's Science Brainery, where science is not just learned but felt in here. Actually, it's not too far from what I want to try to do today, because my real objective is not for you to learn the content, but to get a good feel for it. And that'll certainly be the focus of this video in taking measurements of mass, weight, volume, and density. It's my experience that students learn these definitions often year after year, but just forget them later because they never really have a grasp of what they mean. So, I'm going to try to give you a good feel for what these words mean, and we shouldn't forget that the best way to do this is for you to actually get out and take some measurements of your own. So, here is an outline of our video. We're going to talk about what is matter, and then we'll move into the measurements of mass. And then something closely related to that is weight, and I think weight will help us actually define more about what mass is. Volume is next. I think that's probably the easiest of them. And then density, which I think is probably the hardest of them. So, let's get started. Number one, what is matter? The true scientific definition is anything that has volume and mass. I find that to be a very confusing definition because it assumes that you already know what volume and mass are. If you watch any of my videos, really anything on matter, you know I have a very technical definition for matter, and that is stuff. Matter is made of stuff. All the stuff around you. Desks, chairs, bottles, cameras, the earth. The earth is actually made of rocks, and rocks are made of dust, and dust is actually made of stuff. So, all of this stuff has stuff inside of it. Helium is made of stuff. Water is made of stuff. In fact, you could put those into a balloon. So maybe the definition should be anything you can put into a balloon is matter. I don't know. You can fill a balloon with milk. It's got stuff in it. It's made of matter. You can't fill a balloon with your hopes and dreams. But that doesn't mean they don't matter. Dream big, kids. Dream big. It does, however, mean that our hopes and dreams aren't made of matter. Neither are things like energy, like sound and heat. These things move through matter, but they're not matter. What about air? Here's a good quiz for you. Is air made of matter? Does it have stuff in it? Well, can you put it into a balloon? Yeah, of course you can. So yes, air is made of stuff. Air is made of oxygen and carbon dioxide and water vapor. And these things are atoms of different elements or molecules that make up matter. And all these words, atoms, elements, molecules, they all mean slightly different things. If you're interested, I have a video on models of atoms and molecules. But for our purposes today, we're simply going to call all of them particles. A particle is a generic term that really just means a part of something. And matter is made of parts. Matter is made of all these small particles floating around. We can't see them. They're way too small to see. There's billions and billions of them just in this pen right here. In fact, there's billions and billions of them just really in the head of this pen. So they're really way too small for us to see. But here's a very good definition of what matter is. Matter is made of stuff made of particles. Question number 2 says, what is mass? The definition of mass is, and this is the scientific definition, a measurement of how much matter is inside of an object. Well, if matter is made of particles, shouldn't I be able to measure just how many particles are stuffed inside of something? What about if I count them? Well, I can't, of course, because they're way too small. But what if I could? So let's just pretend for a second that I could get a really powerful microscope or something, or the particles are big enough, or somehow I could count them all. So let's look at this picture. Here's a bowling ball and a beach ball. Both of them are made of stuff. So they both have these tiny particles. That's matter, right? And they're floating around inside of them. So let me count them. Let me see how many particles they have in them. I don't know if you can see all of them, but our bowling ball has 40 particles of matter, 40 particles of stuff. Okay, 40 things inside of it. Those black holes, by the way, are the finger holes where you're supposed to put your fingers in the bowling ball. Don't make fun of my drawing. It's very good, I think. So that's the mass of the bowling ball, 40 particles, right? It has 40 stuffs inside of it. Well, what about the beach ball? The beach ball, if you need to pause this video to count them, you should count 18 particles of matter, 18 particles of stuff inside of it, 18 things, okay? Now, this is a bit ridiculous because obviously we can't count particles. But what it does give you is a good foundation for what mass is. It's counting the matter inside of something. How much stuff is inside of it. Since we can't count particles, we developed a unit that's much larger than a particle that would help us measure what matter is, and we call it a gram. So 1 gram, just to give you a kind of a feel for what a gram is, 1 gram of water has about 1 sextillion atoms in it. That number's written like this. So if you're wondering why we don't count atoms, well, that's the reason why. There's just way too many atoms in a gram to count. But we made up this word called gram, and we measure it using this thing called a balance. Now this is the only type of balance. There's other balances you might have seen. This is the most common type. It's called a triple beam balance. So you put something over here, and then you move these things to find out when it balances. This right here has about 87 stuffs inside of it, or we can now call those stuffs grams because we know what to say now. So this right here has about 87 grams of mass inside of it. So what about weight? I think if we talk about weight a little bit, we'll get a better feeling for what mass is. So question number 3 is, what is weight? The definition of weight is the amount of gravity pulling on an object. Weight is actually different from mass because weight is a measurement of gravity. Gravity is not as simple a concept as we sometimes learn, but for right now, let's just say it's simply the force that pulls everything down to Earth. Okay, it gets a little more complicated than that, but again, for our understanding of weight, that's good enough. Gravity is just this force pulling things down to Earth. So I think of, this might sound stupid, but I think of like little hands coming out of the earth and pulling things down. When I was a kid, I remember this video game. It was supposed to be scary, and you had to walk through this field and think of hands that are pulling down. But okay, anyway, that's what I think of when I think of gravity. Like all these hands are coming up, and they're pulling stuff down, back down to Earth. So don't laugh at me. That's just the way I do it. You do it however you want to. All right. But so let's look at our bowling ball again. Well, our bowling ball has 40 particles of matter in it. So that means it has all these little hands coming out, maybe 40 hands in all, and they're pulling down on all that mass. Okay? And I could measure that if I take this right here, this is called a scale, and I put that bowling ball here, and that hand is pulling it down, that invisible hand, and I can measure how much pressure that hand is putting on this. And I could measure that in pounds. Okay? Sometimes we call it newtons. We measure weight in newtons, newtons of force. But anyway, so that's what weight is. It's a measurement of how much those are pulling down. Well, what happens to my beach ball? My beach ball, there's going to be fewer hands pulling it down because there's fewer particles. So there's 18 grams of mass, so I might have only 18 hands pulling it down. Put my beach ball on here, the hands are pulling down, they're not pulling as forcefully, and so the beach ball is going to have less weight. Okay? Do you see how the difference between those two things? Mass is the stuff inside, and weight is how much the earth is pulling down on that stuff that's inside of it. So there's another way to do this, by the way. This is called a spring scale. Okay, it's still a scale. It measures in newtons. Newtons of force is what we call that. And you just tie something, you put something on here, and it pulls it down. Like here, I got this cup right here. It's probably not the safest thing to do. I have this cup right here, and the hands are pulling it down, remember, and so it's going to show me that this thing is pulling down with 5 newtons of force. And I can look at that right here and see 5 newtons of force. Okay, consider this question. Here we go. So I've got this container of water. I put the lid on it. See here, lid off, lid firmly secured, closed, so I can't lose any water to evaporation. And I'll put my water on my triple beam balance here, which you know that means I'm taking a measurement of mass, right? Mass in grams. And I'm looking at it and I see that it has 449 grams in it. So this has 449 grams of mass in it. Okay, so I'm going to go to the moon and I'm going to take the same measurement. I'm sitting here on the moon and I'm holding my breath, whatever, and I'm taking the same measurement on the moon. And what I wonder is, am I still going to get the same amount of mass? Now, before you try to answer, think of what the definition is. Amount of stuff inside of an object. Does this container still have the same amount of stuff in it, or did I lose some stuff as I went from here to the moon? And if you think about it, I put the top on this thing. I didn't lose any stuff. It maybe kind of evaporated in there. It may have turned to some of it turned to gas. I don't know. Maybe might be kind of floating around a little bit if I shake it or something. But it's still going to be the same amount of stuff in there. So the answer is yes. It's still going to have the same amount of mass. However, if I go to the moon, I have less gravity. By the way, the moon has gravity. Don't let anybody ever tell you the moon has no gravity. Okay, it just has less gravity. When the astronauts jump, they just jump higher and they come down slower, but they still come down. It still has gravity. It has about 1/6 the gravity of Earth. So, does the weight change? Well, weight is a measurement of gravity. So, yes, the weight changes. If you go to the moon, there's still hands pulling down, but now the hands are much smaller, and there's smaller hands pulling down. In fact, the hands are about 1/6. So if you want to figure out how much you weigh on the moon, you would divide that by 6. So I could take my spring scale here. I could weigh this thing. This thing is being pulled down by 6 newtons. Okay, so we can divide 6 by 6, and that's 1. So this thing would be 1 newton on the moon, whereas it's 6 newtons here on Earth. So here's a chart comparing mass and weight. The definition of each: weight is a pull of gravity, whereas mass is a measurement of how much stuff is inside, how much matter is inside. We measure weight with a scale, and we measure mass with a balance. We measure weight in pounds, and we measure mass in grams. Question number 4, what is volume? Volume is the amount of space an object takes up. Or you might say it's how big it is, how voluminous. Girls know this a lot because they use the word sometimes when they talk about their hair, adding volume to their hair, making it bigger, making it more voluminous. So look at our beach ball here again. The beach ball is bigger, it has more volume. Now the bowling ball has more mass, more stuff inside of it, and more weight, more gravity pulling on that mass. But that doesn't mean that it has more volume. The beach ball is bigger. So it's possible for something to be bigger and have less mass in it. There's 2 ways we can measure volume. One is just simply by multiplying the length times the width times the height. So here I have this cube, and if I just take this and I measure that it has it's 2 centimeters. Well, it's a cube, so it's going to be 2 centimeters in height, 2 centimeters in width, and 2 centimeters in length. And so 2 times 2 is 4. And 4 times 2 is 6. So this has a volume of 6 cubic centimeters. Here's a box right here. If we were to cut that box into 1 centimeter cubes, we'd have 1, 2, 3, 4, 5, 6 centimeter cubes. So that one's also 6 cubic centimeters. So that's how we write that. Volume equals 6 cm with a little 3 over it. That means cubic centimeters. And we write that because it's length times width times height. Okay. This box right here, try this for yourself. How many cubic centimeters is that? And you should have got 24. How do I do that? Length, that 3, times width, 4. 3 times 4 is 12, times height, 2. So see, it doesn't matter what order I do it in. 12 times 2 is 24. So it doesn't matter what order I do it in. I can do 2 times 4 times 3, or 2 times 3 times 4, or 3 times 4 times 2. As long as I have all 3 dimensions in there and I get 24 cubic centimeters. A second way we can do this is called water displacement. And here's how this works. First, here's a small little experiment for you can do to test water displacement. First, what you do is you go into your bathroom, you fill up your bathtub until you just can't fill it up anymore. Now, there is a little release on there where you'll notice the water, when it gets too high, it goes through this little hole. So just cover that up with some tape or something so you can get that bathtub just up to the very top. It can't get anything else inside of it, and then get into it. Okay? And then you just tell your parents, hey, Mr. Indris said I could. Okay. No, you're obviously not going to do that. And you know you're not going to do that because obviously the water would get all over the floor. And the reason that happens is because the water takes up space and you take up space. So you're not going to both take up the same space. So the water level is going to go up when you get in. Well, that's the same thing that happens with a graduated cylinder. So if I take this is a graduated cylinder right here, and I have some water in there. If I put something else in there, it's going to go up a little bit. So right now I have 10 milliliters of water in here. That's how much. That's the volume of the water. I have 10 milliliters. That's how much water I have. A milliliter, by the way, equals a centimeter cubed. So it's the same thing. I could say I have 10 centimeters cubed of water, or I have 10 milliliters. Well, let's say I want to take the volume of this paper clip. I can't take length and width and height because it's not a good shape to do that with. See, it has this space in between. Well, what I would do is I would just drop it in my water, and I could see that my water has gone up by 1 milliliter or 1 cubic centimeter. So I could say my paper clip, the volume is 1 cubic centimeter. Okay, let's try an example of that. Here's a pencil I put in a graduated cylinder. How many milliliters or cubic centimeters volume is that pencil? And you may have realized it's 2 milliliters or 2 cubic centimeters. And that's because the water level used to be at 25. And then I put that pencil in, and it went all the way up to 27. So it went up 2 milliliters. Well, this right here is 25 milliliters of water and 2 milliliters of pencil. Okay. So here is a great chart for volume. The definition is amount of space an object takes up. What tool do you measure it with? You can measure it with a ruler or a graduated cylinder, and we measure it in milliliters or cubic centimeters. What about density? Question number 5. What is density? This is the last one we're going to look at. This one is a little bit harder to grasp, but I think when I'm done you can have a good feel for what density is, and I'm going to share with you kind of an easy way to deal with density. But first off, density is defined as the amount of mass in a given amount of volume. So we can more easily write our definition with the words we know. Instead of saying mass, we'll say stuff, and instead of saying volume, we'll say space. So the amount of stuff in a given amount of space. So let's look at our box again. The volume of our box, remember, was 6 cubic centimeters. Let's say the mass is 18 grams. I got 6 cubic centimeters. Remember, if I cut it up into 1 centimeter cubes, I'd get 6 cubes. And I have 18 grams of mass. Well, what does that mean? That means I have like 18 particles in there, or 18 stuffs in there. Remember, so I put 18 little dots in here to represent those things. If you count all those, if you count all those, I promise you there's 18. Well, what's density? If I cut it up into these 1 centimeter cubes, that would be 3 particles or 3 masses per every 1 cube. And that's exactly how I write density. 3 grams for every centimeter cubed. So here's a bit of math for you. You could easily do that if you just say density equals mass divided by volume. My mass was 18, and I divided it by 6, and I ended up getting 3 grams per cubic centimeter. You can remember this formula, by the way, if you remember that density as a heart, and sometimes density breaks your heart. See what I did there? There's the M and there's the V. So that's the formula for density. Mass divided by volume. Of course, this doesn't work if you don't know what a fraction is, or that fractions mean dividing. So you can simply remember this: mass divided by volume, mass slash M slash V, or you can just put this, the M goes on the inside. Okay, it's not the bigger number that goes on the inside, but it's the M. Now I always remember that because the M faces down, and so it's on the inside, and the V lifts up like that. Well, I promise you I'd give you an easier way to remember this whole density thing. And when we talk about density, we really talk more about relative density, and that is, how does something fit with its surroundings? Is it more or less dense than its surroundings? And one way to remember this is just simply, if it floats, it's less dense than its surroundings. If it sinks, it's more dense than its surroundings. So like a balloon floats, so it's going to be less dense. A bowling ball is going to sink, so it's going to be more dense. A beach ball floats on water, so it's less dense than the water. But rocks might sink, or rocks do sink, and so they're going to be more dense than water. And so that's just an easier way to talk about density. If it's floating, then it's less dense than its surroundings. If it sinks, then it's more dense than its surroundings. Let's look at a couple practice questions to see if you got this mass, weight, and volume stuff. What measurement is being taken below? The mass of the apple, the density of the apple, the volume of the apple, or the weight of the apple? And that is a balance, so the answer should be the mass of the apple, A. If you got that right, you're wonderful, you're awesome. You know exactly what you're doing. Number 2, what is this tool used for? A, to measure how much matter is inside of an object. B, to measure how much space an object takes up. C, to measure how much gravity is pulling on an object. Or D, to measure the mass of an object. And you may have noticed A and D are the same answer, so I'm hoping you didn't pick one of those. The answer is C, to measure how much gravity is pulling on an object, or we also call that weight. What is the volume of this cardboard box? Volume is length times width times height, so 6 times 2 is 12, 12 times 4 is 48. And A is the correct answer. If you're looking for more questions, more quizzes, or more things to do with mass, volume, and density, check out my store on Teacher Pay Teachers. So here is some worksheets on some quizzes on volume and mass and density and weight. There's a reading selection right here. You can find that link to that Teacher Pay Teacher site in the description of this video. You can also check out my website at www.indrusscience.com.